Hi there. Today we're going to keep going in Chapter 5 looking at volumes, which is an application of integration. So let's jump right in. So the first thing we're going to define is a geometric shape called a cylinder. What you think of as an ordinary cylinder, like the shape of a can or something, is a general term. In math, a cylinder is really any three-dimensional object that has identical top and bottom sides and then is connected up by some line segments or a plane or a curve as it's stretched up. So you can see at the bottom there's three kinds of cylinders that we're going to deal with mostly. And if the angles where the edges join the top and bottom are all right angles, it's called a right cylinder. So we're only looking at right cylinders because we're going to use this to do some integration problems. So the best example to look at is probably this one, this first cylinder here, where we just have any shape, base 1 and base 2. They're the same shape, and the plane is parallel. And then you can see two very specific kinds of cylinders. Notice that its volume equals area times height. So the area is just the area of the base, and the height is how tall it is. So all three of these just have a height. And depending on the shape of the base, you get different formulas, right? So for a circle, the area is pi r squared. So a circular cylinder, specifically a right circular cylinder, is pi r squared h. And then a rectangular box, they're all right angles. And it's length times width times height. So here, V equals AH. This is the main sort of a general form that we're going to use when we construct the integral. So we're going to use that shape. So now we're going to look at volumes of other kinds of solids. And the way we do this is we take these strange shapes, whatever they happen to be, and we cut them up like we're cutting up a loaf of bread. So if we're trying to estimate the area of this, the volume of this here, the idea is that we can cut it into a bunch of little pieces, compute the volume of each piece, and then sum the volumes. That's what we're trying to do. And so the idea here is that eventually we're going to increase the number of slices, and the volume estimate will get closer and closer to the true volume of the solid, whatever it happens to be. So don't worry, we got lots of detail coming up. So the way we do this is we take this funny shape, whatever it happens to be, and we slice through it with a plane. That's called a cross section. That cross section has an area. So this pink shape here has an area. It must be sliced perpendicularly to the x-axis. You can see here, it's kind of sliced. It looks like it's at an angle, but it's perpendicular. And the idea is that as you take different slices, the area will change. So the area is a function. So if we can find out what the function is, then we can eventually turn this sum of all the little bread slices into an integral. That's what we're trying to construct here. So this is very similar to what you saw in the previous video. So the idea is that you can call them slabs. If you just want to think of them as slices of bread, that's fine. But when we think slice, we think cut through. These are slabs. They're going to have width. And the width of these slabs is going to be delta x, defined the same way it was in Calc 1 and in the previous section. It's just b minus a, whatever those numbers are, divided by the number of slabs, tells you the width of each slab. And we're just going to take different planes and slice through. So it's like px1, px2. You just slice through it with these varying planes. And they're all of equal width. Once you've sliced up the bread, you can pick any point in the slab to use that sample point as the calculation for computing the area. And so you'd have the area times the width. Again, we're calling it height because we're thinking it's like a cylinder, right? We're thinking it's like one of these things, right? Imagine it's laid on its side. Now here we're in the x direction, so our height is really width. So the idea is we cut this thing up into lots of intervals. The width of each interval is delta x. Pick a sample point on the x-axis and cut through, compute the area there. And so the area will be what we call the base, and the height is what we're calling delta x. That will give us a volume of each slab, or each slice of bread, if you want to think of it that way. And so the volume of each cylinder, again, when I say cylinder, I mean the slabs themselves, not the whole thing. So make sure that you got that definition understood. So the volume is area times delta x. If you want to think of it as base times height, using the formula from a few slides ago. So we can approximate the intuitive conception of the volume of the ith slab. So as you slice this thing up, the area changes as you move through, but the area is representative of like the region around that sample point. And that's what this would look like. So the volume of the ith slab, some weird lingo here, is the area of xi star, there's xi star right there, times delta x. So we're just adding up a bunch of volumes of bread slices. And then you just sum all of the volumes. And that's what the summation is for. And then we want to turn this into an integral because we don't want to add a bunch of volumes together. And so what we do is we define the limit as n approaches infinity. So the number of slabs goes to infinity, which means the width of each slab gets smaller and smaller. Eventually, as you get closer and closer, you take the limit. That gives you the volume. So there's the formula. So we're defining volume using this notion. So if somebody says, well, what does the volume of something mean? Because we're looking at solids that might not have a lot of nice characteristics. But as long as we can compute the area of a slab, then we'll be able to use the integral. So we only need to be able to slice it in some direction or another to get a nice answer for this. So this is a Riemann sum, take the limit, and you get the area. So this is the formula we're going to use. All right, well, let's see how to use this. So the first application of this is solids of revolution. So the idea is we have a function, and the function is bounded on the bottom by the x-axis. And we know the limits of integration from 0 to whatever. In this case, it's 0 to 1, but it could be between any two numbers. So the idea here is that this blue region has an area. But what we're interested in is what happens if we rotate that whole thing around and trace out a volume? How do we compute that volume? So the way we do it is we draw a typical rectangle, as we saw in the previous section. Draw up a typical rectangle, and then when we rotate the rectangle, you can see that rectangles turn into disks when they're rotated. We know how to find the volume of a disk, right? It's pi r squared h. We saw that on one of the first slides. So the idea here is that all we have to do is compute the area of this thing, not even the volume, because the height is going to be in our delta x is our height. When we do the integral, delta x turns into dx because it gets very, very thin. So all we really have to worry about is what axis we're on. So here we're on the x-axis. So when the limit goes to infinity, this disk gets infinitely thin, essentially, and becomes just an area. And as we move from 0 to 1, that area gets bigger and bigger and bigger, or it changes sizes. In this case, it gets bigger. And because we can describe the area of the disk as a function of x, that allows us to do the integral. So I just talked about this. What's important is the radius, though. So let's talk about that. You can see that when we take this rectangle and rotate it, the radius of this resulting disk is exactly the height of the function in terms of x. So even though we're talking about a y value, right, the height of this function is measured in y. But we know the function, so we can turn y into a function of x. So that's how integrals work, right? We saw that in Calc 1, that you try to get everything to be in the same variable. But when we try to compute the area of this disk, the radius is whatever the height of the function is. In this case, square root of x. So we plug that into the area function, right? So the area of a circle is what we're talking about. We're talking about the area of this circle right here. Notice the width is delta x, but that turns into a dx, so we don't have to mess with it. Just need the area. Pi r squared. The radius of that circle, the disk, was square root of x. So it simplifies just to pi x. So this is a pretty straightforward problem in terms of doing the integral. So we just plug everything into the formula. Right, the delta x will turn into the dx here when we do the formula. So the volume from A to B of the area of the disk, dx, the area we found up here was pi x. You just plug in pi x. We're going from 0 to 1 because in the graph you can see that the solid is bounded by 0 and 1. This one's real easy to do the integral, right? It's just pi over 2x squared from 1 to 0, which is just pi over 2. So this is, I kind of talked about this in section 5.1. Most of these problems is setting it up. On the homework, obviously, you're going to want to work through it. Once you get it to a definite integral, we already saw how to use our calculators to get a numerical value for the integral. So, but you can see that most of this problem was just setting it up. That's what happens in Chapter 5. The most work you have to do on these problems is just the setup. All right, so let's do an example. Kind of like, let me break down all the steps, right? I just kind of walked you through the process in the previous few slides. Find the volume V of the solid obtained by rotating the region bounded by the given curves around the specified line. So, here's the curve, 4 minus 1 half x. This, we're rotating, y equals 0 is the x-axis, but we're rotating around the x-axis. You have to specify a top and bottom. Because as we've seen, we could have that, you could have two functions, and they could go below the x-axis. In that case, we wouldn't be able to rotate it. So we're going around the x-axis, but it's bounded at y equals 0. And then in the x direction, we're going to be between 2 and 3. So first thing you want to do is sketch the graph of this by hand. So you know the line 4 minus 1 half x. The y-intercept is 4. The x-intercept is 8. So you know what it looks like. And then we're just bounding it between 2 and 3. And then you just like color it in. Then we need the typical rectangle. So it doesn't matter where you put it. Notice the height of the rectangle is the function, right? The function is 4 minus 1 half x. When we rotate this thing, we get a thin disk. And it kind of looks like that. I kind of put it on its side like that. So if you are doing these problems at home, you want to try to sketch these things out. As I said in the previous video, this stuff will get more complicated. And you're going to have to really make sure that you're visualizing things correctly. So it's important, we need to know how to build the volume integral. So we need to kind of know what it looks like. Do we understand the area of this disk? And things like that. So the area of the cross-section, right, so that's the circular cross-section there, the disk. We know it's pi r squared. The radius is the height of the function, right, 4 minus 1/2 x. I went ahead and just distributed this thing out because we know we're going to do an integral, and you don't want to do integrals with parentheses and squares and all that stuff. Remember, you want polynomials when you do integrals. We know that the solid is between 2 and 3. We were given that in the problem, original problem. So you plug everything into the volume integral. Right, so ax dx, we go from 2 to 3. This whole thing is ax, a of x, and then just tack on dx. And then you can attack this integral any way you see fit. I pulled the pi out, did the integral, and you know, as we progress through, I'm going to show less and less of the Calc 1 steps. Again, on a test, I could easily just say right here, stop, once the integral is set up and simplified. Do not perform the integration, because you could just go on your calculator and get these numbers, 23.82. If you're doing it by hand, or if I say I need an exact value, then you need to do the intermediate steps, because you need that pi in there to represent that it's an exact value, because it's an irrational number. So fractions, radicals, pi, those are all things that represent exact values. Decimals, not so much. But that's how you do it. So if you want to pause the video here and go back and do that problem again to make sure you understand it, because in the next example we're moving on to new stuff. There's quite a bit in this section. Or if you want to pause and try the homework problems that look like this, that's fine too. You don't have to do the whole video in one. That's why it's on YouTube. All right, so we can obtain solids of revolution by rotating around the x-axis or the y-axis or some other axis. So it turns out lots of things can happen. So this is a picture of a y-axis disk. And the disks that we use to represent AX do not need to be solid. They can be ring-shaped with hollow central regions. So this is where we start getting into a lot of the visualization. Most students do fine with the vertical integration. But when it starts coming into the rings, and in the next section, 5.3, we're going to see another technique that this really requires that you spend a lot of time setting your problems up. So let's get into it. Find the volume V of the solid obtained by rotating the region bounded by the given curves around the specified line. So here we have x equals 2y and y squared equals 2x. And we're going to go around the y-axis. So you can graph these by hand, sketch them out, or you can use, like I did in the previous video, you can use Desmos. But before we do any of that, because there's no guarantee that these intersection points are nice, let's practice finding the intersection points by hand. So you substitute one equation into the other and solve. So what I did is I substituted this x in here and simplify and solve. This one factors out real nice. So the intersection points are y equals 0, y equals 4. We're going in the y direction. And one other thing you have to do is when we put the limits of integration, the bounds on, you have to make sure that we're writing, that x is a function of y. So you need to have x by itself on the left side. Here, it says x equals 2y, but this one, we need to get x by itself. Make sure you're doing that. It's easy to forget to do that when you're building your integral. Now, we're rotating around the y-axis, so the disk is going to be horizontal. And note that the disk will have a hole in the middle. So its area will be the difference of two areas. A bigger disk with radius r, capital R, and a smaller disk with radius lowercase r. So it'll look like this. So if this is my little rectangle, notice that when we spin this thing around, it's hard to see here, but we spin this thing around, it makes a hollow disk, because what we're really doing is building a big disk and then subtracting a smaller disk from the center. Right? So think about this like if you had a piece of cardboard or something and you wanted to build like a ring out of it. You would take a big piece and then you'd cut out a smaller piece and remove it. That's exactly what we're doing. So that's where this setup comes in, why we have to be so careful. It's really easy to get mixed up when you're doing this stuff. So we're going to have a big ring where the radius is 2y, because that's the outside function. It's the rightmost function. And then our inner function is y squared over 2. Is on the inside. So what we're going to end up getting is a area calculation for the big ring that uses 2y, and an area calculation for the small ring that uses y squared over 2. And so that's what this says, right? The area of this cross section is the area of the outer disk minus the area of the hole in the middle. So you have like a big disk minus something that got punched out of the center. And so here's pi r squared, that's the outer disk. And then pi little r squared is the inner disk. And you can factor pi out. We know r and r because they were given here. So what we do is we just plug in the values of the function. But this is a formula. So, right, just plug in the outer function. Don't forget to square it. Plug in the inner function. Don't forget to square it. Simplify. Now we're ready to do the integral. So what we're doing is we subtracted the areas, and we're just going to do the integral on what we've already subtracted. So the solid lies between y equals 0 and y equals 4. We found that earlier when we did the intersection points. So notice the area of y, we've already computed all of this. Just plug this whole thing in here. You're going to want to factor pi out. Do the integral the way you would normally do a y integral. If I ask for an exact value, it's got to look like that. If you're checking the answer on the calculator, you'll get an approximation. So this is another one that you're going to want to pause the video and try it again, or try problems that look similar to this in the homework. The homework problems are jumbled a little bit because the idea is that that they're not necessarily in the order that the examples that I'm going over are. But you can look in the homework for problems that look similar to this if you want to try to practice this technique. I do recommend that you do this problem again. There's a reason I picked the problems that I do. I think they're the most representative of the stuff that you guys need to know for the class. And most of the ones I do are homework problems, actually. I'm sure some of you figured that out already. Okay, one more major topic that we need to get into. So let's look at what happens when you rotate around a line that is not the x-axis or the y-axis. So here we're going to rotate the region bounded by those curves, y equals x squared and y equals x, around the line y equals 2. So it's easy to find the intersection points, right? Substitute one equation into the other and solve. So everybody can see clearly that we're gonna integrate from 0 to 1. But the bounds of integration aren't the problem. The problem is, what is the area of the resulting hollow disk? So it turns out that here's what the function looks like, but we're rotating around the line y equals 2. Right? We're taking this whole thing and spinning it up. So we have to figure out what this radius is. The outer radius and this inner radius. We have to figure out what these are. So think of it in terms of length. What's the distance between this point, this y, and this point? So you can see that the outer function, remember when we do the disk, the outer function is the largest radius. And it's always top minus bottom or right minus left. So the top function in terms of y is 2 minus this, whatever this function is here. Well, we can see that that's y equals x squared. Right? I mean, we can just see that. And because we're going in the x direction, right? When we do the integration, we're going to go in the x direction. So we want our answer in terms of x. Right? I mean, it's in terms of y, but we're substituting x in. Because the distance is y, but we're integrating in the x direction. So we want x's and constants in our equation when we do the integral. So that's this big R here. The small r is 2 minus, well, that's the line y equals x. So it's 2 minus x. So there's a lot of geometry here. And you really got to think about how we compute distances, how we compute radiuses of circles, and areas of disks. There's a lot of like geometric considerations here. So the outer radius is 2 minus the function x squared is going to be bigger than 2 minus x. So even though x sits above x squared, so if we were finding the area of this, the integral, we'd put x on top. But we're not finding the area. We're finding the volume. And the volume is based on the area of the big disk, not the area of this region. So you can see that there's a lot going on here, right? So let's see what happens when we spin this thing up. What does it look like? So it ends up looking like this, right? It's a big ring that comes up around. I plug everything into the formula. And remember, I'm doing this ahead of time so that I don't have to do 2 integrals. You're allowed to do the subtraction part before you do the integral. If that's confusing for you, that's fine. You can do both integrals separately, but you'll get the same answer. So I just plugged in 2 minus x squared. That's my outer r. And again, the radius has to be squared, so I square that whole thing. Little radius squared is 2 minus x. I just distribute, because I want to do an integral, so I want to distribute everything. Once everything's simplified, I pull the pi to the front. So I just distributed everything, canceled all the terms that I could, got it looking as nice as I possibly could. This is about as nice as you can get it. And once you set up the integral, we know it goes between 0 and 1. Right? We found that earlier in the problem. So it's just the integral of this area function for the disk. Remember, this is the area of the disk. You integrate the area in the x direction to get a volume. So the volume is going to be this. You guys know how to do integrals. We've talked about that a million times. Exact value, approximation. So if you'd like to pause this one and try it again, go ahead and give that a shot. Or if you're feeling good about it, we can keep going. Okay, one more topic. And this is using something called cross-sectional area. So these are not solids of revolution. We're not rotating anything. But the idea is that you take this shape, this solid, and you find some way that you can cut it up, that if you cut it in equally spaced intervals, the shape doesn't change. So we got this weird shape here just as an illustration. I'm not going to do this problem. It's this weird shape, looks like a hat or something. So you can see, looking down on the top, it's a circle. But if you look from the side, it's a triangle. So it's a weird triangle. It's like as you pass through, it's a triangle that gets bigger and then gets smaller. So that is something you could compute by looking at the geometry, setting up relationships, and things like that. I'm going to have you look at a different problem instead. We're going to look at the part of a sphere problem. So imagine we have a sphere. We want to find the volume of the cap. So if you slice it at some horizontal value, some distance from the top of the sphere, what is the volume of the slice? Like the cap that you took off. Right? So imagine it's like a tomato and you're just slicing off a chunk. How do we know the volume of that slice? So this is a great example of a problem that's much harder to set up than it is to solve. I'll do my best to explain how to set it up, and then I'm going to leave it to you guys to solve it because this is a homework problem, and I don't want to give it away. So the first thing you want to do is, so we know that, let me back up a little bit. The slicing itself is horizontal. And if we think, what kind of slices could we make? The idea is that you slice at down H and then you start slicing up. Those would all be equal width. Those would all be circles. So we're going to look at the side view. So this is taking the sphere, and instead of looking at the top, we're going to look at the side. We need to find the radius of those little circles as we take slices. So from the side view, we know that this height is r, and we know that whatever value h is, that from the center of the sphere out to the intersection of the sphere, up to that height h, remember this is going to be h right here, this has to be r minus h. So what it does is it really gives us, it's really the Pythagorean theorem, right? We need to know this radius. R is a constant. R minus h is a constant. And so what you see here, x squared plus y squared equals r squared. Remember, x and y are variables. We need to reduce this problem to either an x variable or a y variable. R is a constant, h is a constant. So obviously we're going to want to do this in x because the radius, as we take slices, and see the little arrow up here? Those slices are rotated this way to make circles. So we need the radius of those little circles. So the typical rectangle sits in here like this way, like in here somewhere. So the idea is we're going to integrate from the lowest y to the highest, right? So this value here is r minus h, and then we're going to integrate from r minus h up to r, right? Because the radius of the sphere is r. So that's r right here. So we go from r minus h to r, making the disk from the rotation is a circle with area pi x squared. So x is a variable. We actually don't care what this length is because we're integrating in the y direction with respect to x. So our bounds of integration are y bounds. So all I did was took the Pythagorean theorem and I'm solving it for x. Well, think about this area formula. It already has an x squared in it. So I don't even need to take the square root. I don't have to solve for x. All I need to do is solve for x squared. So I'm actually done with the setup. So the area here is pi x squared. X squared is r squared minus y squared because it's Pythagorean theorem. And that's how you do it. That as you go up, the r goes with it, and it keeps making right angles. So this always holds. So I set the problem up for you. I'll let you finish it. Remember, r and h are constants, and you should be good to go. All right. I think that's everything. So here's some extra practice stuff for you. If you have any questions, let me know. And Next video, we're going to be looking at a different method of finding volumes. So you guys should be able to do the homework, and just let me know if you need anything. All right. Bye-bye now.